One last thing to discuss in this module is to talk about how work done by forces in the moment relate with the change in energy. Okay, so without any proof, I'm going to give you the expression that relates work with the change in kinetic energy, and that is W is equal to change in kinetic energy. So delta T is T2 minus T1, where T2 is final kinetic energy and T1 is initial kinetic energy. Okay, we have already seen what the expressions for the kinetic energy look like. So kinetic energy is defined as 1/2 mvg square plus 1/2 ig omega square, where m is the mass, vg is the velocity of the center of mass, ig is centroidal mass moment of inertia, and omega is the angular speed, right? We have also seen how to compute the work done by different forces. So in any given problem, if you know the forces and the moment applied and you know the displacement, you can compute the left hand side, which is the work done. And then if you know the difference in kinetic energy, you can equate it to that. Okay, so you can think of work as cause, and you can think of changing kinetic energy as effect. Just as with the Newton's second law, you could think of forces as the cause and acceleration as the effect. Okay, so forces give rise to acceleration, which in turn manifests as change in velocity. Similarly, you can think of work done, which is basically the force done over displacement over a certain distance, that manifests as change in kinetic energy, which relates to the speed, either linear or angular speed. So let's do a couple of simple examples. So let's say I have a particle. It's being pushed by a force F of 5 Newton. Its initial speed is 0 and it travels by a distance of 10 meters. The question is, what's its velocity at this instant? So V sub F, what is V sub F? Okay, final velocity after it has traveled by 10 meters. Now we can solve this problem by using Newton's second law. Okay, we have seen an example of that before as well, but we'll try to solve this particular problem using the work energy approach because it will give us the answer much more quickly. So the first question to answer is, what is the work done? Okay, so work is defined as delta T. So what is the work done? To answer that question, we have to draw the free body diagram and see what kind of forces act on it. So we have force F, we have the normal reaction, we have the mg, and we are neglecting frictional force over here. We already know that n and mg will not do any work because the direction of the displacement is this way, which is perpendicular to n and mg, right? That we have already seen. So the only work done would be due to F. So the question is, what is the work done due to F? That would be, call it F sub uppercase F. That would be F times the distance traveled, that's 10, because the F and 10, the distance traveled is in the same direction. This will be positive quantity, so that will be 50 joule, right? That will be 50 joule. Okay, so we know the left hand side. Now what is delta T? Delta T is defined as 1/2 mv square v final square minus 1/2 mv0 square, which is initial velocity. So notice that we did not use any of this rotational kinetic energy term because here we have modeled this as a particle, and a particle by definition cannot have rotation. So this will be simply 1/2 mvf square. Now we can equate W sub F equal to delta T from our work energy relationship. So that's 50 equal to 1/2 masses. Let's say mass is equal to 1 kilogram. So this would be 1 times Vf squared. So Vf squared is equal to 100. So Vf is equal to 10 meters per second. That would be the answer for this question. So in this case, we have a particle that's basically translating. Okay, now let's do another example. Let's say where we have a disk that's rotating about its center of mass. All right. And what I'm going to do is I'm going to also apply a force here at the periphery of, let's say, 5 Newton, right? And this distance r is, let's say, let's call it 1 meter, okay? And I will also actually add a motor now over here, which I will say applies the torque of, I don't know, let's say 10 Newton meter, okay? And let's assume that this disc or the gear or the wheel or the pulley or whatever it is was initially at 0 speed. So omega 0 was 0 radians per second. Okay, now the question is what is the angular velocity or the angular speed after, let's say, 10 revolutions. Okay, after 10 revolutions. That's the question. So clearly we have a torque applied on the disk. There is an external force that's also trying to rotate in the clockwise direction. So both the torque as well as this external force are cooperating to essentially rotate this gear or the disk over here, right? And eventually you expect it to pick up some speed. So the question is, what is that speed? Okay, so there's work being done. Let's relate that work done to the change in kinetic energy. So first thing is, what is the total work done in this case, right? So what is the work done? So the work done over here can be determined by first drawing the free body diagram to look at all the forces that act on it. So we have 5 Newton force this way. We have about center of mass, the torque T of 10 Newton meter. Okay, and then we have the reaction forces Gx and Gy. Okay, so those are all the forces, right? Now Gx and Gy will not do any work because those forces are applied on a fixed point, and the fixed point has zero displacement, so there will be no work done due to Gx and Gy. The only work done would be due to 5 Newton and the torque 10 Newton meter, right? So the work done due to 5 Newton would be equal to what? So let's call it W sub F would be equal to the force itself times the displacement, right? Now this is tangent to the path. So what is the displacement? Well, we know that this radius is 1 meter. Okay, so the radius is 1 meter. That means the total circumference is 2 pi times 1, right? That's the total circumference. And if it undergoes 10 revolution, then the total distance traveled would be 10 times of that, right? So that's the work done in joules by the force, the external force. So that will be what? 5 times 2 is 10, 100 times pi. So that will be close to 314 joule. Okay. Then we also have the work done due to the torque. What is the work done due to torque? We know that that is torque times the delta theta, right? So what is that? T times delta theta. So T is given to you as 10 Newton meter, and delta theta would be equal to 2 pi times 10, right? So that would be 2 pi, because 2 pi is radians for one revolution, that times 10. So we get 200 times pi, right? So that's what? 200 times 3.14, so that would be 628 joule. Okay, that will be 628 joules. So the total work is equal to total work done due to force F plus work done due to torque. So that's 314 plus 628. So what is that equal to? Okay, so let me calculate that. So that's 942 joules. So that's the total work done. Okay, now we have to relate it to the change in kinetic energy, right? That's our basic formula. So W is equal to delta T. So let's now find delta T. So delta T is equal to final kinetic energy minus initial kinetic energy. Initial kinetic energy is 0 because it's at rest, right? So what is T2? T2 is equal to 1/2 I omega final square, right? Because minus 1/2 I omega 0 square is 0. Now notice over here that from the kinetic energy expression that we have over here, we have only picked the rotational term, not the translation term, because V sub G, which is the velocity of the center of mass over here, is 0, because G is a fixed point. So this would be equal to 1/2. Now we'll model it as a disk. Let's say the mass is given as 1 kilogram. So this would be mr square over 2 times omega f square. So that's 1/2 times 1 times r is also 1 squared divided by 2 times omega f square. So we get omega f square over 4. Okay, that's your delta T in joules. So we would equate it to the work done, which is 942. So what do we get? So 942 times 4, and then we do a square root of that. So that gives us 61.38. So we get omega f equal to 61.38 radians per second. That's the answer we get. Okay. All right. So we did an example of a pure translation. We did an example of a pure rotation as well, right? Okay. Now let's do a slightly, more involved problem. Let's say I have a pulley here, I have another pulley over here, and then there's a cable that goes over the pulley, and there's a block tied here, and then this comes down, and let's say there's a person here who's pulling this down with a force of 5 Newton. Okay, somebody who's pulling with his hand of 5 Newton, and let's say this is 1 kilogram mass. Okay, this is 1 kilogram mass. you know what, let me make this to be 15 Newton, and this is a 1 kilogram mass. Okay, I want this force to be more than the weight of this. Okay, so 15 Newton, that's 1 kilogram. So my question is, number one, what is work done by tension in the rope? B, what is work done by gravity on the block? And C, if this started with zero velocity, 0 meters per second, after it has traveled, let's say after the block has traveled by let me say 1 meter, what is its speed? Okay, what's its speed? So those are the three questions we're trying to answer. So let's first try to get the part A and part B done, work done by the tension and the gravity. So first thing is to draw the free body diagram, right? So I've got the mg, and then I've got the tension, and clearly this is assuming that there's no slack in the rope. Then, you know, all throughout from here to here, the tension would be same, which would be same as basically this force F of 15 newtons. So we know this tension T is actually equal to F. Okay, those are the only forces. So part A is what is the work done by tension. So we'll call it W sub T. That would be equal to integral F dot dr, right? And we can clearly see that the displacement direction is up, the force of tension is also up, both of them are the positive direction, so that means it will be a positive quantity. So that would be nothing but the tension times the distance traveled, and we know the distance traveled is 1 meter, so 1 meter, so we'll write that as 1 meter over here, that's in joules. And the F is 15, T is same as F, right? So that's 15 times 1 joule, so that's 15 joules. Okay, so that's the work done by the tension. What is the work done due to gravity? Work done due to gravity would be the force of gravity, that's mg, so that's 1 times 10, so that's 10 Newton, times the distance traveled, which is 1 meter. But now the force of gravity is pointing downward, the displacement is upwards, so it will be a negative quantity, so that will be minus 10 joule. Okay, so that's number part B, all right? And then the part C is, after the block has traveled by 1 meter, what's its speed? So we can use the work energy relationship, W equal to WT. W is equal to W sub T plus W sub G equal to 1/2 mv2 square minus 1/2 mv1 square, where this will be 0 because initial velocity is 0. So this is 1/2 m is 1 times v2 square, and WT is 15, WG is minus 10, so that's my 15 minus 10, so that's 5 equal to 1 over 2 v2 square. So v2 square is equal to 10, so v2 would be equal to v2 would be equal to what? So if you do a square root of 10, what do you get? Square root of 10 is equal to 3.16. It's equal to 3.16 meters per second.